Hello and welcome. Today we're going to be discussing the solution to the problem cow splits from the first contest in the 2026 bronze season. In this question, we are dealing with square strings, and we say that a string x is square if there exists another string y such that x is the sum of y with itself. So let's take a look at some examples. So the string cow cow is a square string because it is the sum of the string cow with itself. Alpha star alpha star is a square string because it is the sum of alpha star with itself. And in this question, we are given a very long string composed of cow and its two other rotations. And we are allowed to remove any square subsequence of the string. And the question that we want to answer is how many removals do we have to do to this string in order to reach the empty string? Or if it's impossible, then we will print -1. So the first observation we want to make in this question is that if the string has odd length, then this task is impossible. And the reason for this is that square strings must have even length, right? Because they are the sum of a string with itself. That means the length of a square string is going to be 2 times y. So it's always going to be even. So if the string that I'm trying to remove these square strings from has odd length, it will never reach the empty string, which has even length. So in the case where the string has odd length, we just return -1 and move on with our lives. The second observation is that if the string itself is square, then the task just requires one operation because we can simply remove the entire string. For example, if the problem gave us the string cow cow, we could remove the entire string in just one operation by removing the square string cow cow, right? So a subsequence could be the entire string in one shot. And then the third observation that I want to make is that if a string has even length, the task always requires at most 3 operations. And how do I know that it requires at most 3 operations? Well, we can do a sort of clever hack here and simply remove all of the C's. So all of the C's will form a, um, a square string. All of the O's will form a square string and all of the W's together will form a square string. So if we simply remove the square string with all the C's, then we remove the square string with all of the O's, and then we remove the square string with all of the W's, then we're left with the empty string, and that only takes us 3 operations. So where does this leave us? With just these 3 observations alone, you can get partial credit on the question. Namely, it is not necessarily optimal to use 3 operations, but what we can do is we can either print out 1 operation if that's possible, or in the worst case, we can print out 3 and we'll always be off by at most one operation. If we want full credit on this question, we need to make a fourth and crucial observation. The fourth and final observation is that if the string has even length, the task always requires at most 2 operations. To see this, let's work through an example together. So we're going to take a string all jumbled up like this, and we're going to chop it up into a more understandable format. So what we're going to do is we're going to first split it into 2 halves. So we're going to grab the first 9 characters and put that on one side, and the second group of 9 characters, put that on the other side. And then we've additionally taken every group of 3 characters and broken them up so we can clearly visualize each distinct grouping. And what we're going to be doing is we're going to be pairing these groupings together and analyzing how many of the letters are overlapping. So what we want to do is we want to create a square string where 1/2 of the square string comes from the left-hand side, and the second half of the square string comes from the right-hand side. So let's take a look at this square string. The way we created this square string is we took a look at this pairing and we said, well, cow and cow are the same. Those 2 groups, they contain the identical letters in identical ordering. So we can add both of those to our square string, right? They both start with the exact same letters. If we go to the next grouping, we can see that they do not contain the letters in the same order, right? Cow has a different ordering than WCO. But what we can see is that two of the letters appear in the same order. In particular, in this example, CO appears in the same order in both strings. So while we can't add the entire string to our square string, we are able to add the characters CO. So I'm going to add CO to my square string on the left-hand side, and I'm going to add the characters CO to my square string on the right-hand side. And what we're going to see when we do this is that cow CO has the same beginning as cow CO on the right-hand side. So far, we're fulfilling the definition of a square string where both halves of the string have to be the exact same. And then just to go through this example one more time, we can again see that we have two strings formed by rotations of the word cow that are not in the same order, right? OWC is not in the same order as WCO. But two of the letters are in the same order. WC is in the same order as WC on the right-hand side. So we can add WC to both sides of my square string, and we can see that we get the square string COW, COWC on the left-hand side, and then the same exact thing on the right-hand side. So the sum of this is a square subsequence. And what's really neat here is since in every portion where we weren't able to grab the entire string, we left behind just a single character, and that single character was the same. Whatever didn't get included in the first square string becomes itself a square string. So a W was left behind in the second group here. And again, in the second group on the right-hand side, a W was left behind as well. So we get a W in both cases. Same thing for the last grouping. We have an O left behind in the last group on the left-hand side. We have an O left behind on the last group on the right-hand side. So we get the square string WO, WO. And between these two square strings, we can see that every letter has been included in these operations. So we can see that these letters are going to be operation 1, whereas these letters are going to be operation 2. So the key idea here is we are constructing a greedy algorithm that is able to produce a very long square substring that includes most of the letters, and every letter that's not included in that square string forms a second square string, which produces the letters in operation 2. So all we need to do in this question is actually check if the string is odd or even. If it's odd, print -1. If it's even, we just have to check if the string itself is a square. If the string itself is a square, we print 1 and all characters are removed on the first operation. Or if that doesn't happen, then we apply the process that we described in observation 4 and produce the two square subsequences that allow us to remove the entire string in just 2 operations. So in fact, we never need 3 operations. We can always do it in just 2. And in order to convince yourself of this observation, I strongly recommend working through several examples by hand. Again, you're going to create a string, you're going to split it into 2 halves, and you're going to try to collect 1 half from the first side and a second half from the second side that match. So feel free to pause the video and try this on a few examples to convince yourself that this idea does actually work, and then we're going to jump into the code. So now let's jump into the code, and we're going to see that the actual implementation here isn't all that bad, although the one thing that's annoying is we are going to have to take a lot of substrings. So we're going to keep chopping up the string into little substrings and comparing to see which letters match, right? We have to be able to check, do all of the letters match, or do just 2 of the letters match? If 2 of the letters do match, which 2 match, right? So when we're comparing like cow and WCO, we see that the first 2 characters in this string match the last 2 characters in this string. Or it could be the opposite, where the last 2 characters from the left-hand side match the first 2 characters from the right-hand side. So we're going to have to check all of those cases. So there's a little bit of casework here, even after we spot the critical observation. So let's begin with the impossibility case. We're just reading in n and then this string of size 3 times n. If there's an odd number of elements in our string, we're just immediately going to return -1 and we don't have to do anything else. Otherwise, we're going to break the string into two halves exactly as we've done here. And this allows us to check both the first case where we need one operation and the second case where we need two operations. Because when we go to check if S is square, S itself being square is equivalent to the first half of the string simply being equal to the second half of the string. So if half 1 is equal to half 2, we can print out 1 and return the operations. Operations here is just an n times 3 long array filled with 1s, and we're going to leave most of them to be 1s, except in the case where we need two operations. And in that case where we need two operations, any element that's included in this second set of square strings will be updated to a 2. So operations will either be a string of all 1s, or a few elements in operations will be updated to a 2, as you see right here. So anywhere it's a 1, that corresponds to the first square subsequence. Anywhere it's a 2, that corresponds to the second square subsequence. But in the case where S itself is a square, the entire thing just stays all 1s, and we print out the string of all 1s. If we failed this check, then we continue on with observation 4, which is all other cases can be done in just two operations. So in this case, we're going to loop over every single group here. So we're starting a counter at 0, and then this input to the range function just means that I'm going to skip count by 3s. And the ability to skip count by 3s is just going to allow me to look at each group of these length 3 substrings. So I'm going to check first, do all 3 characters match? And if they match, so that would be this substring in the first half being the same as this substring in the second half, then I don't have to do anything, right? That's what we saw with this cow. Nothing is added to operations, or no elements with value 2 are added to operations. They all stay in operation 1, and we can add the entire substring to the first square sequence. However, if they don't all match, then the best thing we can do is get two characters. And there's two possibilities for how we could match two characters. Either the first two characters in the first half match the last two characters in the second half, or the opposite. So the the last two characters in the first half match the first two characters in the second half. And in either case, we update the character that's been left out to join the second group of operations. So we're saying whichever character doesn't match, that is going to be set aside for the second square substring, or subsequence, I should say, to be more precise. Now, you can make this code a little bit simpler, right? At the end, we just print out 2 and the operations. You don't technically need to pull out this case where we are analyzing if the first half is equal to the second half. If you really wanted to, you could combine these two cases together. But I think it's a little bit easier to understand if we separate out this first observation where the second and first half are exactly equal. To see what the code might look like if we remove the first case, we have an updated code here on the left-hand side where we do the exact same thing as we were doing earlier, but instead we just print out the maximum value in operations. So if operation stays entirely positive 1, then we will just print out 1. If some 2's get introduced, then we will print out 2 operations instead. So this can be a little bit of a shorter way of writing the code. The most common question I expect to receive on this question is, how do we come up with ideas like this? And the key idea is that we want to analyze lots of test cases. So if you're thinking that you might not have been able to come up with this idea, what I want you to observe is that the most fruitful and helpful test cases are going to be some of the shortest test cases. So even if you just start analyzing test cases that are maybe just 6 characters long, and you try to split this into square strings, you are very quickly going to force yourself into sort of some of the same observations that we came up with when analyzing this example, right? We have to match this OW with this OW, and this C matches with this C. So even just analyzing very small test cases, and lots of them, is going to be a very helpful tool in discovering this critical observation. So on that note, thank you so much for watching the video. I hope you have an absolutely wonderful day, and I'll see you in the next one. Bye-bye.